time for the moment you've all been waiting for, average atomic mass. This is where we do some math. The atomic mass, the average atomic mass on the periodic table, is the weighted average of all existing isotopes for that element. There are lots of different kinds of averages. In your math class, you probably talked about mean, median, mode the most. Those are technically all averages. And usually we think of like average as mean, like that's the one that we call average. Median and mode are also a type of average. And weighted average is a fourth type. That's what we're going to be talking about today. The weighted average depends on the abundance of each isotope, meaning which isotope influences the average the most by being the most common. There are many types of averages, again, such as mean, median, and mode. Average atomic mass is a different type called a weighted average. So you're learning about a fourth type of average today. You actually already know about weighted averages. You just probably didn't know that that's what they were called. For example, think about your grades. If your grades in my class were a 90, a 90, a 90, and an 80, would the mean average of your grade be closer to a 90 or closer to an 80? It should make sense when you look at it that if you're taking the mean of 90 plus 90 plus 90 plus 80 and dividing by 4, because there are so many 90s in there, the average would be closer to 90. It would be closer to 90 because there are more not 90s. Because 90 is more common. As another example, if your electric bill is $100 a month during the colder months, so like 33% of the year, and it's $200 a month during the rest of the year, so the other 67% because you're running your air conditioner, will your average yearly electric bill be closer to $100 or closer to $200? Well, if for 67% of the year, it's $200 a month, then it's going to be closer to $200 per month because that happens more often. Let's do an example that's actually chemistry, but I think you might be starting to see what we're getting at here, that these averages, this average of 90, this average of 200, those are weighted averages where like we could take the mean and figure out exactly what it comes out to be, but we're going to see that because there's something much more common in the data that keeps popping up over and over again, it's weighing the average down toward a certain value or up toward a certain value, depending on how you look at it. So let's look at a chemistry example. Nitrogen has two stable isotopes. 99.6% of all the nitrogen atoms in the universe have a mass of 14. The other 0.4% have a mass of 15. Remember that when we write that notation of an element, hyphen, and a number, that number is the mass number. So the 14 and 15 there are mass numbers. Would the average mass be closer to 14 or closer to 15? Well, if you look and see that 99.6% of all that nitrogen atoms in the universe are mass of 14, that should tell you that it should be closer to 14 because it is more common or more abundant. And if you look at your periodic table at nitrogen and find what is the average atomic mass listed for nitrogen, it is 14.01, which is pretty darn close to 14. Now, there are a couple problems for you to try yourself. I want you to pause the video, try these two problems yourself, and then play the video, and I'll help you check them. But you need to try it yourself. Pause the video, try it yourself before you watch me go over it. Pause the video, try it yourself. So if you read this question, it gives you a bunch of data, and it's asking you for the average atomic mass of lead. That means the mass on the periodic table. We know that the mass on the periodic table is going to depend on the weighted average of all of these numbers. We're not just going to take the mean of 205.974, 207.977, 206, 203. We don't just take the mean of those four numbers. That's not how we're going to get what's on the periodic table. Just like with this nitrogen, the number on the periodic table is not the mean of 14 and 15. The mean of 14 and 15 is 14 and a half. That's not what's on the periodic table. We didn't take the mean. We let the average be weighted down by how common nitrogen 14 is. Same thing here. We're not going to just take the mean, and we don't even right now have to calculate it. We're just trying to figure out what's it going to be closest to. Well, what we know is that the most common one is going to affect what the weighted average, that average on the periodic table, is going to be. So if we look at these percents, 24.1, 52.4, 22.1, 1.4, the highest percentage is going to tell me which one's the most common, and that's going to be the one the average is weighted toward more. So 52.4% is the highest percentage. So that mass that goes with the 52.4% is what the average atomic mass should be closest to. And we know that because it is most abundant. Meaning, again, when we say the most abundant, we mean the most common, which in this case is the highest percentage, which was the 52.4. In number 2, we see a table that lists relative abundances of a particular element on the periodic table with the mass of each isotope. It wants to know what element would most likely have this isotopic composition, and how do you know? So if we're going to know what element it is, that means, again, we're going to need to be checking the periodic table. What are we going to look for on the periodic table? The only information we have, right, is masses. So we need to decide, what are we going to look for on the periodic table? I guess we need to look for mass. So which one of these masses in the chart is going to be the most useful to us? Which one is going to give us the best information when we go looking at the periodic table? It's going to be the one with the highest percent. That's going to be the one that the periodic table will be the closest to. The mass that goes with the highest percent. So our percent is 96. That means we need to look for something close to 39.962. If you look at your periodic table, you can find a couple to choose from, basically. There's a argon 39.95. There's potassium and calcium 39.1 and 40.00. And then the next thing after that hops all the way up to 44. So it's probably one of those three: argon, potassium, and calcium. And why don't we examine those three kind of in isolation? Like, I'm just gonna copy them down so I can take a good look. Now, all of these are close to 39.962. We have to decide which one of these is the closest and also the best. I think if we look at these numbers in the chart, we can see that like 39.10 is a lot further away than either 39.95 or 40.08. That's a lot further away from the 39.962, so it's probably not going to be potassium. But then choosing between argon and calcium, if you're looking just at what's closer, 39.95 is closer. But the problem with just looking at that is that if you think about how averages work, these other percents still come into play. Like they're still going to affect the weighted average. They're going to drag it in a certain direction. They're not going to drag the average as hard as this 96%, but they will drag it. And if we look, all the masses that go with those percents are higher than 39.962. So they're going to have, these are going to have a little bit of an influence on the average atomic mass, and they're all going to pull that mass to be a higher number than 39.962. They're all going to pull it up because all of those numbers are higher than 39.962. Whereas 39.95 is less than 39.962. And there's not actually a way for an average to be less than all the numbers you add up, right? Like if we go back to that example with our grades, if your grades are 90, 90, 90, and 80, can your average, your mean be 70? That's not possible. That's not how math works. That's just not how math works. The average cannot be less than your lowest data point. It can't be outside your range. So it can't actually be argon either. It's got to be calcium. And the way we know is that it is closest to the most abundant isotope while still being inside the range of the chart. The data in the chart. That's important. If it's outside of that range of the chart, it doesn't work. You can't have an average 70 if all of your grades are 90, 90, 90, 80, right? Like you would know if you checked home access and it said you had a 70 average, but all your grades were 90, 90, 90, 80, you'd be like, something is wrong. That's not how math or averages work. So let's look at the next page. Recall the mass found on the periodic table is a weighted average of all the occurring isotopes for that element. That weighted average accounts for abundance, how frequently a particular isotope occurs. For example, the most common form of carbon is carbon 12. Therefore, the weighted average is close to 12 instead of being close to the less frequently occurring isotopes, carbon 13 or carbon 14. Like if you look at a periodic table, the weighted average of carbon is 12.01. Carbon 13 and carbon 14 exist, but if we just took the mean of 12 plus 13 plus 14, that mean comes out to 13. But that's not the weighted average on the periodic table for carbon because most carbon is carbon 12. Carbon 13 and carbon 14 are really rare. So you're not really adding up 12 plus 13 plus 14. You're adding up all of the 12s, all of the 12s, plus 13 plus 14, and then you're dividing by how many of all of those there are. I just kind of wrote an arbitrary number of 12s, but that's going to be much closer to 12.01 because we have way more 12s. In reality, it's not like 6 12s and a 13 and a 14. It's like 99% 12s and like less than 1% 13 and 14 each. But you get the idea. Okay, there are some steps for calculating average atomic mass. You need to put the given information into a table, convert the percents to decimals. To do that, you divide by, hopefully you know this from middle school, but just in case you forgot, you divide by 100. You're going to multiply that decimal that you just came up with times the mass for each isotope, and then you add together all of those products from each isotope. So for example, A sample of zinc contains 48.89% zinc 64, 27.81% zinc 66, blah, 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 blah. Conveniently, all of that information is in a table for you. The table makes it so much easier, so much easier. And what we're going to see is that the masses right here, notice, where do these masses come from? They are right over here in your isotope notation. Again, remember that element dash number notation is telling you the mass number. So those masses came from the name of the isotope. Now, there's a couple different ways you can do this math. Either way, there's steps we're following where we got to turn it into a percent into a decimal first. Remember, to turn a percent into a decimal, you divide by 100. That's what you're technically doing. If you want to just do it by hand, that really just means you're moving the decimal place 2 times. It does get a little tricky when it's a 1-digit or decimal percent. You gotta still move the decimal twice. So just keep an eye out for that. Like here, it's a 0.62%. You still have to move the decimal twice to turn that percent, whoops, into a decimal. So it becomes 0.0062 as a decimal. Your next step is to multiply the decimal that you just found times the mass. So like we're going to multiply 0.4889 times 64, and we're going to get some number. We're going to multiply 0.2781 times 66, and we're going to get some number, so on and so forth for this whole part of the chart. Now, here's where I give you some good news. This is actually, there's a slow way to do it and a fast way to do it. The slow way is to hand write this whole thing and use a calculator and go all the way down, which will work for you, obviously. But since we're doing a lot of our work on our computers right now anyway, why don't I give you a faster way to do it? And you're going to find that the calculations we end up using for a lot of stuff in this class, you can do it the way I'm about to show you. So you can actually use Google Sheets to act like a calculator. Oops, that says decimal. Like you can go to your Google Drive and just click on like File, New, or I think it's New, and then you click Google Sheets, or you can even like open an old Google Sheet and start a new one. But basically you can type the chart from your notes into a Google Sheet and use this as a calculator. So like you could hand type 0.4489, 0.2781, and so on and so forth like that. But if you know what you're doing, you don't have to do all that in your head. Once you have the data in the Google Sheet, you can actually, if you hit the equal sign, it'll turn into like calculator mode basically, and you can tell it, I want to take this number, and it says A2 because it's saying like here's A and here's 2, and it's finding that in the grid. So I want to take this number and divide it by 100. That's how we turn percents into decimals, right? But then the really cool part is if you copy that cell and paste it down, it'll copy not the number answer, but the formula. So now if we look at like this one, it's doing A3, which is this divided by 100. This one's doing A4, which is this divided by 100. So this is a much faster way to get your calculation done. And then similarly for the product, we know that we want like this number times this number to go right here. Well, you could slowly type like equals 0.4889. Oops, that's not even it. 489 times 64. You could type it like that, similarly to how you would type it in a real like handheld TI-84 Plus or whatever, and you would get your answer. But then you'd have to like type it exactly like that again for this one, and then that like takes a while. If you know what you're doing in Google Sheets, you can actually hit that equal sign and then tell it, I want this cell times this cell. And then if you copy and paste it all the way down, again, it won't copy and paste the answer. It'll copy and paste the formula, the equation. So like here, it says it's multiplying B3 times C3, these two numbers that we wanted to multiply. Here, it's telling us it's multiplying B4 times C4, these two numbers we wanted to multiply. So it's doing all this work for us. And we can absolutely still like keep track of all of this in our like notes page, handwrite out all these answers. In fact, you may have to do like a version of that anyway on a quiz or a test. But to actually like calculate it, even though you're still gonna have to show your work on paper, the actual calculating part of it can go a lot faster for you if you know how to use Google Sheets properly. And then finally, our last step is to add all of these products together, which again, you could like tell Google Sheets, okay, equals, and I want to do 28.7296 plus 18.3546 plus 2.7537. Like you could type all of that out and you would get the right answer, but it would take you longer. And also then you run the risk of doing a bunch of typos, which could throw off your whole answer. Instead, you can actually type equals and then look, Google Sheets even suggests it for you. Sum of D2 to D6, and it's like highlighting that it wants to do these cells and take the sum of them. That's actually exactly what we want. So there you go. If you add them all together, which again, if you know what you're doing with Google Sheets will do it for you. If you add them all together, you can get that 62.8995. Yeah, I assume most of my students do not know how to use Google Sheets to do this, which is why I thought I would go ahead and just show you this big old shortcut that you can use. So you're welcome for changing your life. I'm going to recommend using Google Sheets to present using Google Sheets as a calculator frequently. That's my go-to for stuff like this, especially where you're doing a big old chart of data. It's so much faster in Google Sheets. And I assume a lot of you don't have a TI-84 Plus at home anyway. So here you go, new method. So I did go ahead and show all my work in my booklet. If you didn't write it down while I was showing you the Google Sheets, I'll point out that this is a YouTube video and you can just back it up, find that data and copy it down yourself. You'll notice now there are in front of you quite a few questions to try by yourself. There are a couple where you have to fill in the data from the question straight into the chart yourself. There's even one where you have to draw your own chart. So have fun with that. Just want to make sure you know what you're doing. Again, remember when you're looking for a mass to go in this column, that is what these numbers on your isotope are. Those are your mass numbers. That should end up going in that chart over there. So just a thought, a little bit of help for you there. Yeah, that's average atomic mass. It's so easy.